So you're likely wondering why we care about light if what we're after in this course is the discussion of electrons and their behavior. Well, it turns out that electrons themselves act like quantum particles. Einstein's photoelectric effect experiment demonstrated this. Electrons, like photons, can behave like waves and like particles at the same time. We say that electrons have discrete or quantized energy states. So, what does that mean? Like photons, electrons can only have certain energies. Their energies are governed by more complex equations than photon energies, so we won't calculate those in this course. But what we will say is that electron energies exist across a spectrum, and we can think about the spectrum as being sort of like books on a bookshelf. I'm going to draw out an imaginary bookshelf. We'll use just simple lines to represent shelves on a bookshelf. Perhaps here's one shelf, here's a second, a third, a fourth, a fifth, and a sixth. Now, I drew successive lines closer to each other than the previous set, not because I'm a bad artist, which I am, but rather because around an electron's distribution in the atom, successive bookshelves are closer together the higher we get. Remember that the universe is lazy, just like I'm lazy. I'm going to want the lowest bookshelf to be the most accessible, and I'm going to number bookshelves from there on up. The lowest bookshelf I'll call shelf number 1, and I'll number each successive shelf in turn in increasing order, from 2 to 3 to 4 to 5 to 6. Atoms will place electrons on shelves in the simplest way that they possibly can. Just like I'm lazy and will put an electron on the lowest possible shelf that I can, an atom will place an electron in the lowest possible bookshelf that it can possibly muster around its nucleus. Suppose that an atom has one electron to place on an energy bookshelf around it. It's going to want to place that electron on the lowest possible energy shelf, the one closest to the ground, like shelf number 1 here. Just like books cannot exist in the space between bookshelves, electrons cannot exist in the space between successive shelves around their nucleus. So an electron can sit on one shelf, but it can't ever occupy the space in between shelves. What electrons can do, however, is move from one shelf to another. This little electron here could be promoted to another shelf higher up if it's supplied with enough energy. We have to supply energy to move that electron, again, because our atoms are lazy and don't want to have to use any more energy than they absolutely must. So suppose that we shine some light on this electron, and light is governed by principles of both particle nature and wave nature. As a particle, it packs some energy. It turns out that light can transfer energy to an electron and make it move from one shelf to another. We can place our electron on a higher shelf if we can shine light with just the right frequency at that electron. We say that an electron absorbs light. It absorbs the energy of light and is able to move from one shelf to another. The caveat to this is that the energy supplied to our electron to allow it to jump from a lower energy shelf to a higher energy shelf around this electron bookshelf must be exactly equal to the spacing between bookshelves. Again, an electron can't just hover in midair between two shelves. If we tried to do that, it would just fall down to the shelf that's nearest. So, in order to get an electron to jump from one energy level to another, we have to supply just the right type of energy. If I had shown a different color light at this electron, perhaps I might have allowed it to move to a different energy shelf. Suppose that I shown blue light instead of yellow. According to our electromagnetic spectrum, blue light has more energy than yellow light. Perhaps blue light would have caused our electron to move to this energy shelf, the third one, rather than the second. Absorption is a process that requires just the right amount, not too much, not too little, but just the Goldilocks amount of energy supplied from light and absorbed by an electron to get it to move from one energy shelf to another along this bookshelf. Alright, so I just erased everything, and now what I've got is an electron that's sitting on the third energy shelf of its electron energy bookshelf, and we have removed any light source that had been supplying that electron with energy in the first place. So, all that electron has to support it being on the third energy shelf is energy from its atom's nucleus alone. Remember that our nucleus and our atom are lazy, so our atom isn't going to want to supply an electron with the energy needed to stay on that third bookshelf for very long. As soon as the light source is removed, that electron is going to jump back down to its ground state. We call the lowest energy level the ground state because it's the bottom floor of our electron energy bookshelf. And any states above that, any shelves that are higher than that ground level, are excited states. So right now, we'll say that our electron is in an excited state. As a result of the removal of a light source that was supplying this electron with energy, this electron isn't going to want to stay in its excited state for very long. It's going to want to immediately jump back down to its ground or lowest energy state. An electron can't just jump from one energy state to another, though, without supplying some sort of energy, as that would be in violation of the first law of thermodynamics. In order to go from one state to another, from this third shelf back down to the ground or first shelf in this example, an electron needs to shed some energy. To shed energy, an electron emits a photon. We call this process emission. A photon is a packet of energy. In an emission process, electrons shed or emit a photon, a packet of energy, in order to shed their excess and move back down to their ground state, their lowest energy state.
This phenomenon of absorption and relaxation or emission of photons to move electrons across these energy shelves was validated experimentally in the 1880s through the Balmer series for hydrogen. In hydrogen's bookshelf for electrons, we see a similar makeup to the one I sketched just a moment ago. What we find experimentally, and will replicate in the laboratory, is that if we excite electrons from various hydrogen atoms to either the 6th, 5th, 4th, or 3rd energy shelves, that upon removal of an excitation source, those electrons relax back down towards their ground state. They might do so by taking a roundabout way. For example, they can all relax back down to the 2nd energy level first, and from there make their way back down to the ground state energy level. When they do this, they just so happen to shed photons of light that fall within the visible region of the electromagnetic spectrum, so that we can see these photons that are being emitted with our naked eye. When an electron transitions from shelf number 6 to shelf number 2, we see a violet line. When an electron makes a transition from shelf 5 to shelf 2, we see a dark blue line. From shelf number 4 to number 2, we see a teal line. And from shelf number 3 to number 2, we see a red line. This is called a line spectrum for hydrogen, and it's one of the earliest pieces of evidence that electrons are confined to discrete energy levels. In fact, the existence of this line spectrum is predictable. We can calculate precisely what wavelength the electrons transitioning from the 6th, 5th, 4th, or 3rd energy shelves down to the second ought to emit in terms of photons as they relax. The way that we calculate this is through what's called the Rydberg equation. The Rydberg equation looks as follows. 1 over the wavelength of light of a photon emitted in a hydrogen atom is equal to a Rydberg constant called R sub y. This constant is multiplied by a quantity that's given as a difference of fractions. The first fraction is 1 over our final shelf squared. This is the shelf to which an electron moves around a hydrogen atom. The second fraction is less 1 over our initial shelf squared. This is the shelf from which an electron originates. So let me identify what each of these terms means. On the left-hand side, we have a fraction where in the denominator, we've got the wavelength given in meters of a photon that is produced by an electron moving down energy shelves. This is a wavelength of emitted photons for a hydrogen atom specifically. On the right-hand side of this equation, R sub y is a constant. It's called the Rydberg constant, and it has a given value that I will always provide to you. I'll never make you memorize constants. The value for this constant is 1.097 times 10 to the positive 7 inverse meters, or meters to the minus 1 power for units. In the term by which that Rydberg constant is multiplied, the denominators of the respective fractions are shelves. This is the final electron energy shelf, N sub F for final, and this is the initial energy shelf, or starting energy shelf, for an electron around a hydrogen atom. So let's do an example of how we can calculate the wavelength of light emitted from an electron's transition, specifically a transition for an electron around a hydrogen atom that relaxes from the 6th energy shelf to the 2nd. I'm going to take advantage of this Rydberg equation and plug in quantities. I don't know a wavelength yet, so I'm going to keep 1 over wavelength on the left-hand side of this equation. I do know that the Rydberg constant, is a constant value. 1.097 times 10 to the 7 inverse meters. Now, in parentheses, these fractions are populated 1 over the final shelf squared. The final energy shelf, or the shelf at which this electron winds up, is the 2nd shelf. So we're going to say shelf number 2 and square it. In the second fraction in this term, in parentheses, we have 1 over our initial shelf, or the shelf from which this electron originated. This electron originated in the 6th energy shelf, so we're going to use n is equal to 6 here and square it. If we had reversed the order of this process, we'd end up with a negative value at the end, and all we have to do is just drop the negative sign. So ultimately, we've got on the right-hand side of this equation 1 over 4 minus 1 over 36. If we punch all of that into our calculator, 1.097 times 10 to the 7 multiplied by the quantity 1 over 2 squared, or 1 over 4, minus 1 over 6 squared, or 1 over 36, what you should end up with as a result is 2.438, keeping 4 significant digits, times 10 to the 6th power. The units are the same as the units we have up above, meters to the minus 1 power. Inverse meters are 1 over meters. That's all equal to 1 over wavelength. Now, we have to solve for lambda, our wavelength, in the first place. We have it in the denominator of a fraction on the left-hand side, and what we do to undo that fraction is to take the reciprocal of both sides. When we take the reciprocal or flip the fraction, we get lambda by itself. But what we do to one side of a mathematical equation, we do to the other as well. So if we took the reciprocal or flipped the left-hand side, we need to flip the right-hand side too. In other words, we need to put 1 over 2.438 times 10 to the 6th power on the right-hand side. And that's something we can punch directly into our calculator. What we end up with should be 4.102 times 10 to the minus 7. That has units of meters to the minus 1 flipped. So, what does that look like? 1 over meters to the minus 1 is the same as 1 over meters, which if we simplify that complex fraction, just returns meters. So we've got an answer that seems reasonable, a wavelength with units of meters. If we wanted to convert this to nanometers, we could multiply by 1,000,000,000, 10 to the 9th power, and what we'd end up with is 410.2 nanometers. Either one of these is a sufficient answer to the question, since we did not specify which units we'd like to use. But regardless of the result, we can say that the electron moving from shelf number 6 to shelf number 2 around hydrogen must emit a photon whose wavelength is 410.2 nanometers. And sure enough, if we investigate the Balmer series for hydrogen, what we find is that the transition from the 6th energy shelf down to the 2nd energy shelf results in the emission of purple wavelength of light. 410.2 nanometers surely falls into the range of violet on the electromagnetic spectrum. So we can verify that our calculations match with the experimental results. This is the first piece of evidence that verifies that electrons must behave oddly and are subject to exploration by manipulation with light. The seeming ability to calculate the energy levels and the energy transitions of electrons around the hydrogen atom led Niels Bohr to attempt to generalize this to other atoms aside from hydrogen. In Bohr's model of the atom, Bohr suggests that an electron moving down an energy level increases that electron's proximity to the atomic nucleus. In other words, an electron becomes closer to the nucleus of an atom the lower in energy level it gets. But why is it then that an electron isn't simply pulled into the nucleus of an atom? If an electron is negatively charged and the nucleus of an atom is positively charged, and because opposite charges attract, one might think that an electron would just be drawn in to a positively charged nucleus. And then what happens if there's more than one electron around an atom? Do they all get to fit on one shelf? Or do they have to spread themselves out among multiple shelves? The model that Bohr creates for the atom looks like this. Electron energy shelves aren't really shelves, they're more of orbits around the nucleus of an atom. These orbits extend outward from the nucleus in concentric rings, and the size of these rings can be calculated. Bohr's model of the atom helps to explain atomic line spectra and can be generalized to some of the light atoms on the periodic table. But it's not completely sufficient to describe all of the nuances and weirdness of electrons as a whole. Nonetheless, Bohr still received the Nobel Prize for his model of the atom. Later in the 20th century, different experimental and empirical evidence comes forward that contradicts Bohr's model. One such piece of contradictory evidence is the Heisenberg uncertainty principle. Werner Heisenberg showed mathematically that it is impossible to know both the location and the momentum, or velocity, of a quantum particle like an electron. There's an upper limit to how precisely we can know these two things simultaneously. And because we can't see an electron with our naked eye, the best we can do is rely on indirect experimental evidence that's subject to our own shortcomings. What's more is that these tiny particles, like electrons, can behave simultaneously like particles as we've discussed them so far, but also like waves, similar to how a photon behaves. In fact, quantum mechanics tells us that everything has a wavelength. It's just that when things get really big, like bigger than an electron, those wavelengths become negligible. We can calculate the wavelength of any particle we'd like, given that we know something about its mass and how fast it's moving. We do this by taking advantage of some of the work of Louis de Broglie. The de Broglie wavelength allows us to determine the wavelength of any particle. We can calculate the de Broglie wavelength with this equation. The wavelength of a particle, lambda, now for a particle like an electron, is equal to Planck's constant, that fundamental physical constant of the universe that we used for the energy of a photon, now used for a particle as well, divided by the mass of that particle and the velocity with which that particle is traveling. Here, wavelength is now specific to a particle. This is a particle's wavelength in meters. H is Planck's constant. Again, it has a value of 6.626 times 10 to the minus 34 joules times seconds. Little m in the denominator is the mass of a particle given in kilograms. And v is the velocity with which that particle is moving, given in meters per second. If we have knowledge about a moving particle, specifically its mass and its velocity, we should be able to calculate the wavelength it's got. On this slide, I've asked you to calculate the wavelength of two objects in motion. One of them is a baseball being pitched with a velocity that equates to 44 meters per second. I'll do an example calculation in a little bit. For right now, I'll ask you to see if you can recreate this calculation for yourself. You should end up with a wavelength for a baseball of 1.06 times 10 to the minus 34 meters. This is unbelievably, imperceptibly small. A batter facing a pitch at 44 meters per second cannot blame their inability to hit the pitch on the wavelength of a baseball. But when we calculate a wavelength in a similar fashion for an electron moving close to the speed of light around the nucleus of an atom, what we find is that the wavelength becomes more appreciable. To calculate the wavelength of an electron in motion around an atom, we can plug it into the de Broglie equation from left. Planck's constant divided by the mass of an electron, 9.11 times 10 to the minus 31 kilograms. And the velocity of that electron, 1/10 the speed of light, 3 times 10 to the positive 7 power meters per second. If we plug all of that into a calculator, we come up with a wavelength for an electron in motion of 2.42 times 10 to the minus 11 meters. Another way to state that is 24.2 picometers, PM. This dimension, 24.2 picometers, or 2.42 times 10 to the minus 11 meters, is appreciable. In fact, if we refer back to our diagram of a typical atom, we said earlier that the approximate dimension of the diameter of the electron cloud around an atom is on the order of 10 to the minus 10 meters. Something that's 10 to the minus 11 meters would fall somewhere in the radius of this electron cloud. What this de Broglie wavelength suggests for an electron moving around an atom's nucleus is that the wavelength of that electron is appreciable compared to the size of an electron cloud. In other words, an electron that's moving at this speed could be found anywhere over on this side of the atom. There's no way for us to pinpoint that electron because it indeed acts like a wave that's got a wavelength that takes up an entire half of an electron cloud. Therefore, it's impossible for us to confine an electron to a singular path. The best that we can do is say something about the likelihood of finding an electron in a given area or a given cloud. Thus, modern quantum mechanics is developed. Because both the Heisenberg uncertainty principle and the efforts of Louis de Broglie seem to contradict Bohr's model of an atom where electrons orbit a nucleus in discrete concentric patterns, we need a new set of mathematics. An entirely new field of physics needs to be developed in order to explain some of these phenomena and to deal with the mathematical predictions that are put forth. This new branch of physics called quantum mechanics will help us reconcile what electrons do and where they're likely to be found. No more can we deal in absolutes like the Sith. We now have to deal with probabilities. And this notion of dealing with probabilistic natures is what we'll embark on next as we talk about quantum numbers that give us an idea of where electrons are likely to be located.